All right.
I'm speaking about something that's being developed for supernova neutrinos. In this case, no standard interactions and how it can change observables in DUNE, for example, the Manhattan. But also talk to you a little bit about how NSI is intimately connected to the development of neutrino astrophysics, and with very interesting facts. And yeah, you enjoy. The outline of the talk is I will review a little bit about the supernova mechanism and neutrino emission, and how to use different phases of neutrino emission to understand the combustion evolution. The basics of neutrino propagation in dense astrophysical environments, assuming not everybody is familiar with it. So a few interesting facts about the historical developments of these ideas and how they are intimately connected to NSI, and how the presence of NSI, which is the main result, may affect observables at the Deep Underground Neutrino Experiment in future supernova explosions. Okay, so first talking about supernova. So supernova is an event, an explosion that happens in the end of the life of very massive stars, like stars 10 times heavier than the sun. So along its life, the star burns its fuel, like the basically produces energy by making fusion of light elements and producing heavy elements. At some point, the core of the star is dominated by iron. In each case, like it's not energetically favorable anymore to burn iron to release energy to counterbalance the pull of gravity. So literally the star will collapse because you cannot counterbalance the pull of gravity. So there is an implosion. The outer layers of the star fall above the iron core, which as time passes become more and more dense and more incompressible. And what happens is that the outer layers will literally fall in the iron core, incompressible fall, and will bounce back. And when they bounce back, they produce a shock wave, and the shock wave is energetically enough. It will lift up the outer layers and produce the supernova explosion. Neutrinos are intimately connected to this process because the theory to describe the process right now, it shows that the shock waves, when they are propagating outwards, they stall at some point, like 300 kilometers from the core, and if we don't have, if the shock wave cannot be re-energized, the supernova will fail. And who energize the supernova are the neutrinos. So basically, electron neutrinos, mostly electron neutrinos, they come behind the shock wave, deposit energy, re-energize the shock, and the shock goes again and disrupt the outer layer. So basically, the supernova is people say, is a neutrino bomb. So supernova produce lots of neutrinos. Actually, 99% of the binding energy, gravitational energy of the star is emitted in form of neutrinos in more or less 3 stages. So the first stage, which encompasses like the first 10 of milliseconds, like 50, 60 milliseconds, is called the neutronization burst phase. This neutronization burst phase is very interesting because actually, as the shock wave propagates in the media, it disrupts the iron nuclei. So there will be many free protons, free nucleons in the environment. So these free protons start to absorbing the free electrons, and then you produce the neutrons that will compose the future neutron star, and emits lots of neutrinos. At the same time, like as the star, the core is basically kept stable because of the fermion, the degeneracy pressure, the electrons. So if you are absorbing the electrons, you are decreasing the stability, and like this process emits a lot of neutrinos, to decrease the stability of the core and enhance the collapse. So the neutronization burst phase is very interesting because from the simulations we understand that these the signal of this very characteristic in the luminosity of electron neutrinos, and it's much higher than the other neutrino flavors. It's independent on the supernova mass and the equation of state. So you should observe this shape for a range of different sizes and mass of the star. And therefore, because it's so robust, it's sensitive to new physics. So we can do lots of study of new physics. So in these papers, I study neutrino magnetic moments. Today, I'm going to talk about NSI, but it's very interesting to study new physics. So the other phase of the supernova event are the accretion, which takes like the first second, basically. And basically, like the shock waves still stall and the outer layers are falling. So as the outer layers falls to the core, it heats up the material in the core and they start to produce neutrinos of all flavors, in basically equal luminosities. And then you have a later stage of the cooling that all neutrinos are also emitted. It's basically the cooling of the proto-neutron star that's starting to happen. These are much more complicated to study in new physics because these signals have strong variations with the supernova mass and equation of states and dynamics and many parameters which we have no control. And also like complications related to neutrino refraction because here matter effects are basically dominated by electrons, protons, and neutrons. So neutrons are propagating a very standard background. Here neutrinos are propagating a background that matter potential from the neutral currents with other neutrinos often start to be relevant. So the flavor evolution is very uncertain. So it's very hard to study new physics from these other two stages. But if I have time, I'll talk a little bit about them in the end. So supernova 1987A is the only supernova from which we detected neutrinos. So a galactic supernova usually we put as a benchmark distance like 10 kiloparsec, are rare, maybe optimistically once or twice per century. The supernova 1987A was the first one visible from the Earth without the telescope in nearly 400 years since Kepler's time. So I'm not sure that everybody saw with the naked eye, everybody noticed, but the astronomers, they say that the supernova was visible to the naked eye. It was produced it happened in the Large Magellanic Cloud, which is 50 kiloparsecs away, is kind of out of the Milky Way. Neutrinos were detected by 3 detectors, basically, like the TAMU and IMB via water Cherenkov, and liquid scintillator detector in Baksan, in Russia. And of course, like as you can see from the plots here, like the scale here is in seconds, like neutronization burst happens in tens of milliseconds. So from these data, we actually don't have sensitivity to understand to study the neutronization burst.
May I ask the question?
Yeah.
What sets that millisecond time?
Huh?
Where does the time come from, that milliseconds? What sets the time scale?
What sets the time scale? Yeah. So basically is the time that the supernova is passing by the shock waves passing by the iron core, associating the how do you say the iron nuclei, liberating the protons in the environment that will absorb the electrons and emit the neutrinos. At some point, after a few milliseconds, the shock wave stalls, and then you start to have the accretion. So,
but that time is not enough for the shock wave to go through the core. Milliseconds. I mean, it's a sound wave, right? Shock wave, speed is sound.
yeah, like
I would assume that core is pretty big, right?
no, the core is like a few tens of kilometers, 200 kilometers. So, like the shock wave can propagate.
Well, it's still the shock wave should take about a second to go through. Not millisecond.
But that is the time scale for the neutrino emission, right? When he showed the neutrino emission on the previous figure.
Right, but what sets the time scale of millisecond?
But there's 2 phases, right? That's the initial phase, the neutronization burst, right? The milliseconds, and there's the thermal emission, which is the tens of seconds, which I think you're thinking of associated with the shock wave.
So what does set the time scale of milliseconds? Where does the time scale comes from?
Oh, I think that just has to do with that capture coil.
Yeah,
I should let him talk.
The capture thing, like you have the amount of protons, like suddenly you have a lot of protons free and they start absorbing the electrons and then they
I
Like
see,
it
so
saturates.
waves comes like a bunch of
Yeah.
proto, and then the time
Yeah.
scale is really, okay.
Yeah, they absorb
Yeah.
and then it saturates, like then you don't have any more like so much free proton.
Mhm.
That's what
Yeah,
sets
got
it. Yeah. So so a bit of the neutrino propagation dense astrophysical environment. Thanks for the question. So all of these started with solar neutrinos, which were very important for us to understand the how neutrinos propagate in astrophysical environments. Like basically, what really started was like the experiment run by Ray Davis in the home state mine. So Ray Davis was measuring all neutrino fluxes using Orion, and then in his own words, he defined the solar neutrino problem, that is the fact that the sun produces about a third as many energetic boron 8 neutrinos as expected. So 2/3 of the neutrinos produced in the sun, that was predicted by this other. So this is the Ray Davis. This is the John Bacall in the home state mine. And John Bacall predicted some flux, and Ray Davis was detecting a third of that flux. Okay. So to address this problem, many solutions were proposed based on neutrino properties, including, like, of course, the neutrino oscillations and the neutrino magnetic moments. And also astrophysical solutions about properties of the sun, which is like everything, like, so even like many people propose that the sun was already dying. So that's why the rate of reactions was decreasing, and that's why we'll detect 1/3. And other people just propose that, oh, it's astrophysics, you cannot be so precise, 1/3 is just order 1, so it's fine, there's no problem. So all sorts of things were proposed here to address this problem. But then, like, one of the solutions proposed was stood out as particularly elegant, which was the neutrino resonant flavor conversion in the matter, which is the famous MSW effect. So very quickly, like, I'll talk a bit of the MSW effect. Short review on neutron oscillations. Okay, like everybody knows, neutrinos have mixing, neutrinos have masses, and because they have masses, and so and the weak eigenstates, neutrinos are produced in weak interactions. They are not eigenstates of propagation, so because they are not eigenstates, they change with time. And the probability that the neutrino flavor is, the amplitude is related to the mixing angle by this mixing matrix in a 2x2 approximation. We have a 3 neutrino case in reality, but in a 2x2 approximation, the amplitude is related to the mixing angle. The phase is related to the difference of the mass square of the eigenstates. So this is neutrino oscillations in vacuum. Neutrino oscillations in matter, it complicates a little bit, but still quite simple. Like neutrinos interact in matter with electrons via charged current. Neutrinos interact with electrons via charged current with interactions. All neutrino flavors interact via neutral currents with all the particles in the medium. This doesn't affect oscillations because it's a common phase. It affects oscillations. So when we are going to describe oscillations in matter, basically we have the Hamiltonian vacuum. So the Hamiltonian vacuum, Hamiltonian in the Hamiltonian vacuum in the mass base is rotated by the mixing matrix. We can write like this: the Hamiltonian matter is the Hamiltonian vacuum plus a term that comes from the matter interaction, neutrino matter interactions, which is proportional to the electron number density, because only this diagram influences. So you can write this Hamiltonian in this is a 2x2 approximation, which is a good approximation for the sun. For supernova, we have to go 3x3, but let's talk a little bit about the sun. In the sun, as you see, like basically so neutrinos are produced at high densities and they decrease slowly. The density slowly decreases. You don't need to bother about numbers. Right now, I just want to give an idea that the density is very high. So when the density is very high, this term is very large because it depends on the density. All the others are constant. So it's very large, it dominates. So the electron neutrino is actually the heaviest neutrino state in matter. So the heavy state in a 2x2 approximation, we call it nu2. Okay. So the electron neutrino is related to nu2 at dense matter. This term, so these dashed lines are the diagonal elements. This one is constant, this one is decreased linearly. So as it goes down, at some point it crosses. Okay, it crosses the eigenstates. So these dotted lines are eigenstates; they never cross. So the eigenstates, you see, the new eigenstate in matter. First is related to electroneutrinos. After they cross, these diagonal elements cross, it's related to the other flavor of neutrinos, not electroneutrinos anymore. So at this point, you have a sensation that you had a flavor conversion, and that's what is called the MSW resonance. When these two elements are equal, so they cross, and the eigenstates which are produced, the flavor composition changes at that point. So this is the MSW resonance. And if this resonance is crossed adiabatically, so this Hamilton is changing with time for a neutrino. As the Hamiltonian changes, the eigenstates also change, but if the eigenstates, so if the Hamiltonian changes slowly enough, so if the density, the rate in which the density is varying, is much smaller than the density of the frequency of neutrino oscillations, then this resonance is adiabatic. You basically have no, you have no, these eigenstates remain the same, more or less. So all that matters is that electroneutrinos, they were produced in the sun as nu2. Nu2 reached the vacuum. At the vacuum, nu2, the electron component in nu2 is only 1/3. So that's why only 1/3 of electroneutrinos survived and reached the Earth. So this theory is very simple. It's our effect, and it describes very well like the disappearance of 2/3 of the boron 8 neutrinos. Okay, but but the neutrinos have 3 flavors, as far as we know, and so you have, instead of 1 delta m squared and 1, remember the resonance condition is when these two things are equal. I don't know. You have 2 delta m squares. You have 2 delta m squared. So you have 2 resonance conditions for the electroneutrino. And also in the 3 flavor approach, the mixing matrix is much more complicated in the sense that you have more mixing angles, and also you have the freedom to define the hierarchy. So normal hierarchy means that nu1, which is the nu3, which is the eigenstate with the least electroneutrino component, is heavier, and the inverted ordering is when the nu3 is lighter. For supernova neutrinos, we need the 3 flavor approach. We have, because supernova reaches. Put the profile. So let's say for the sun reaches. So this is the density in grams per cubic centimeter. The sun reaches more or less 10 to the 100 grams per cubic centimeter. Supernova, the core reaches 10 to the 13 grams per cubic centimeter. These are very these are nuclear density is very high. So you are going to, so in the sun, you will not go to one of these resonances. That's why the 2x2 approximation is okay. But for the supernova, you need to take into account 3 flavors. So what's going to happen is that instead of having 1 cross between the flavor diagonal elements, you have 2 crosses. Okay. Of DU with these other plates. So you have 2 resonances. In the normal ordering, it happens both for neutrinos. In the inverted ordering, 1 happens for antineutrinos for technical reasons. I don't know in detail. So, but what I want you to understand is that all that matters here is that, okay, neutronization burst mostly nu e because of the peak. You remember nu e in normal ordering is basically nu3. So we know that the initial flux of nu e, the probability that it will survive in the detector. So this initial flux of nu e is related to nu3. The probability that nu3 will be detected as nu e is u3 squared. So, and the other flavors are basically given by u e2 u1, which is 1 minus 4. Because of unitary, you can write like this, and multiply by initial flavor of the initial flux of the other flavors. So this UE3 is very small because U3 has basically no UE component. It's like 2%, and so basically for normal ordering, most of the features that we see in the neutronization burst for electron neutrinos will disappear. So remember, we have a peak, and so probably that peak will disappear. For inverted ordering, 30% of the flux, for inverted ordering, electron neutrinos are produced as neutron. So the probability that initial flux of electron neutrinos survives here is like 30%. And then you have a component that comes from the other flavors also. Okay. So basically, these are the ways you can compute the flavor, the flux at the Earth. So to show, yeah.
I'm assuming this is dependent upon the energy of the neutrinos. So what energy are you considering for this?
Yeah, so supernova neutrinos, they have an average energy of like 10 MeV. Starting with 5 MeV that we detected, between 5 MeV and 50 MeV. So for all energies, you satisfy this conditions, because the density is very high, so you go through a whole range of density events at some
most of
point.
the energy is following.
Yeah.
Okay.
So for all energies in the spectrum, you'll be following the same logic. So I did not tell you, but so just to give you an idea, like the H resonance happens at like 10,000 grams per cubic centimeter. The resonance happens at 10 grams per cubic centimeter, more or less. So this is, yeah. So as you can see, like the sun doesn't reach these. In the place where neutrinos are produced, the sun doesn't reach. So we only go through this, but supernova will go through both of them. So in supernova, you need the three flavor approach. Yeah. So basically, I'm going to show the effect of how like the spectrum of the fluxes. I'm going to use DUNE. DUNE is a 40 kiloton liquid argon time projection chamber. So basically, we are going to detect μe via the interaction with liquid argon. I'm not going to use hyper-K. I put here just for completeness, but hyper-K detects μe bar. And remember, in the neutronization burst, the most interesting thing is the μe. So basically, DUNE will be the powerful tool to study this. And you can see that because very little of the initial flux of electron neutrinos survives, then for normal ordering, the peak completely disappeared. And for inverted ordering, because much more of the electron neutrino survives, the initial peak is still there. So that's basically the standard way that DUNE is supposed to distinguish between mass orderings using supernova neutrinos by having the peak or not. So it's a shape analysis, like the normalization can be anything, but at least by the shape, you are supposed to be able to detect this peak or not. So NSI will mess up with these, so that will be the message. So effect of non-standard interaction. Effect of non-standard interaction. So yeah, there's a very rich history behind neutrino matter effects, and NSI is very connected to these. So usually people say that non-standard interactions, neutral current, non-standard interactions were first proposed by Wolfenstein, I believe, like that's what. But at least in these, for neutrino propagation between source and detector, like the first to touch this hypothesis was Wolfenstein. At that time, he was calling it flavor changing neutral currents. So in his papers, so we can see here in the abstract, so at that time, like neutrino oscillations was a nice hypothesis, but people thought it would be very improbable, not very likely. So Wolfenstein, he wanted to show that even if you have massless neutrinos with no oscillations in vacuum, you still can have oscillations in matter if the currents have an off-diagonal piece connecting with the neutrino type. So if you have flavor changing neutral currents, what today we call NSI, you have neutrino oscillations in matter even if you don't have neutrino oscillations in vacuum. So Wolfenstein started with massless neutrinos. By the end of the paper, he was treating massive neutrinos with mixing vacuum that can have neutrino oscillations, and he added the matter term, and he had all the components, like all the ingredients to solve the solid neutrino problem. But he did not do, like in his conclusion, he basically says that, oh, neutrinos suffer matter effects, but neutrino oscillations between the sun and the earth it takes much more So basically, the whole propagation of neutrinos is in vacuum. The propagation of neutrino inside the sun compared to the distance between the sun and the earth. So these cannot address. These matter effects cannot address the solar neutrons problem. So it took more like 8 years for Mickey Evans-Minor come with the proposal that became like this MSW solution, and that was particularly elegant. So, but after 1985, 86, when Mickey Evans-Minor proposed, still other authors proposed interesting alternative solutions based on massless neutrinos and NSI. These are some examples. These are very interesting papers. Very interesting papers, and but all the solutions were basically ruled out because of the Kamlan results in 2002 or 2003, I don't know, I think it's 2002, in which Kamlan showed that there is neutrino oscillations in vacuum because you have very little matter between the reactors. And so Kamlan is a experiment in Japan that measured reactor neutrinos and showed that neutrinos can oscillate. They saw the oscillation pattern in the data. So in the following, in the rest of the talk, what I'm going to show is that the mechanism of resonance conversion of massless neutrinos and forever changing neutral currents, although cannot solve the solar neutrino problem, it can still occur in supernova. And yeah, these guys started to discuss this, and now we did it we continued it. So how come massless neutrinos? So neutrinos are not massless. Why I'm talking about this can happen in supernova? It's basically because at very high densities, the matter potential are so much higher than the vacuum terms that basically neutrinos are massless. So the whole evolution of neutrinos is, if you have NSIs, is dictated by the NSI. So at that environment, in very deep in the core of the supernova, neutrinos are basically massless. So we can use these ideas proposed by these guys to check if some conversion due to this can happen in the supernova. So, we can relate the strength of the NSI to the density of electrons, protons, and neutrons in the medium. So the NSI is a combination of NSI due to electrons, NSI due to protons, and two quarks U and E, and neutrons, and respective quarks. So to show the effects, to illustrate, basically we assume only D quark NSI, like that we only have non-zero D quark NSI. And then by only put these guys non-zero and relating the number of protons, electrons, and neutrons by this YE, which is called the electron number fraction per nucleon, because this is the number of nucleons. And also assuming that electrons and protons are in the same amount for charge neutrality. Yeah.
Do the number densities of electrons, neutrons, protons vary relative to one another significantly in the vicinity of the proto-neutron star?
Yeah, it does.
Okay.
And that's exactly why this is realizable there, because this will be non-trivial, let's say.
YE will change.
YE will change.
Sure.
Okay. NSI will not change, 2 will not change, but YE will change, and this will make it change. So neutrinos will feel like this Hamiltonian will change.
Good. And so the assumption that you've made about the D quark only interaction, you made a different assumption, say U quark only. Would this
Yes.
evolution look different?
No, it would be basically the same qualitatively. Like numerically, it would change a little bit the bound and so on. But if you put only U quark NSI instead of 2 minus YE, you have 1 plus YE.
But if YE has some non-trivial shape dependence, if you could test that.
No trivial shape dependence. So what I know, like what I'm using is basically this YE, the correct simulation. So go to the proto-neutron side is very, so here outside is very simple, like it's a constant, but here it changes.
Okay.
And basically it changes for the interesting thing that we were discussing. Electrons are being captured by protons and becoming neutrons. And this is becoming a neutron star slowly. So you keep the number of nucleons, but you decrease the number of electrons. So neutrinos are produced exactly where this YE is dropping. So when the more the YE drops, more neutrinos are being produced. So what happens is that so neutrinos are producing very in low Y and slowly goes to very high Y. So this thing will change. If this thing crosses one along the way, then you have a new resonance. So for instance, like just this happens for this range of NSIs, but I will talk about what happens about 0.33. It doesn't change the result. So for example, if epsilon tau d is 0.2, okay, 0.2. Neutrinos are produced at YE 0.2 also. When you put this together, this is like 1.8. But then when they reach 0.5, put this together, this is like 0.6. So they literally, like in this range of parameters, they cross one, and you have a new resonance condition. So you would have a third resonance in the core, in the presence of NSI. This resonance, so why the off-diagonal elements? Yes, because the off-diagonal elements, they dictate how adiabatic will be this resonance. So the transition will be effective or not. You can estimate, like in the two-flavor approximation, you can estimate like the adiabatic parameter. This has to be much higher than 1. You can do this calculation. And you can see that if this epsilon e tau d is much bigger than 10 to the minus 5, this will be bigger than 1, and you have effective resonant conversion. So
I might have a question. So I think, I'm confused. So if you change the coupling from D to like some other like E or U, like how would that change the entire, like I understand it will numerically probably change the bonds, but the physics have something interesting, or does it not undergo this resonance condition when you have like a different coupling?
yeah, that's a good question. So if you change U, the physics will be more or less the same. The results will be the same. Like you could give the whole same presentation like just talking about U. If you put electrons, then nothing changes because the standard NSI already is electrons. So you wouldn't have any non-trivial relation between the standard NSI and like the standard matter potential, sorry, the standard matter potential. So it would be basically if you put electrons there, like in this Hamiltonian, you would have just like what epsilon E. This will probably shift the position of the resonance because now instead of 1, this is like 0.9, 0.7, I don't know, this difference. So you would shift a little bit the position of these resonances. Okay, they would happen. But you would not change anything, any result in the end, because as long as they occur, it will get the same result. So what really changes here is what gives you like a new one. Then that will change the results. Otherwise, it's pretty robust. So you can shift, like you can shift these diagonal elements and so on. And yeah. So yeah, you can compute these and divide. So these are the new energy of water. It's much more messy now. But it's very simple to see what's going to be the result. So for example, for normal watering in the standard scenario, what you have is like mu E is mu 3.
Yes, I've got question.
Yes.
Maybe he should mute. You can tell him to mute.
I think he said I have a question.
Oh, he has a question? I thought this was background. You can ask.
You have, so excuse me, you have a question. No. Yeah, okay. So it's much more messy, but you see that, for example, from this part to vacuum, it remains the same. H resonance, L resonance, everything. Okay, now you have a new one. Why? Because for the rest of the process, everything is the same. But in the beginning here, because of the variation of Y, the new tau is heavier than new E. So when they are produced, instead of new E being the heaviest due to the matter potential, now new tau is the heaviest due to the NSI plus the Y. variation. So now you are detecting so most of the neutrinos produced is nu E in the neutronization burst. So now instead of having a flux of nu3 reaching your detector here, you have a flux of nu2. So this will change completely. For inverted order, instead of having nu2 as in standard case, you have a flux of nu1. So this will change the result. So basically, yeah, as I said, instead of UE3, you have U1, UE2. For one. Instead of one E2, we have one E1. E1.
So, yeah, I have a question. So suppose you have a sterile neutrino, and then this thing can be marked, right? Like all the resonance pictures. So
Yeah.
can you really distinguish your NSIs from the existence of a sterile neutrino? If there is a fourth neutrino form, and suppose the mass is of the order of EV, and you can access it supernova.
If I can distinguish.
From your, so how do I know, like I'm seeing what you are saying that NSI is clear making this. So suppose I bring a fourth component. So can you?
To give you this answer, I'll have to do the thing, but yeah, I think so. If you add a fourth, so all the other neutrinos will be heavier in matter than the sterile one. Sterile one has no matter. So if you are producing nu E, which will be the heaviest, it will be nu4 because nu4 has the more mass. So basically, yeah, all the neutrinos will disappear. You would see even so
Mixing angle. There will be some mixing angle again.
Yeah, there will be some mixing angle. So you'd see much smaller number of neutrinos than I'm seeing here because you see we are producing. So basically, the sterile neutrino has no interaction with matter. So there is no matter potential for him. It would be the lowest energy eigenstate. So then in matter, he would be related to the new one. Right. And then the electron neutrino would be related to the nu4, which has the biggest mass. So the nu4 would come to the Earth. So instead of seeing so then you completely disappear with any neutronization burst peak. So basically, these would be like UE4, which is 0.00000 something. So I assume you would suppress much more the number of events. You wouldn't see this peak, so it would be different from NSI.
You can distinguish.
Yeah, in principle. I mean, all of these doing the detection maybe will be a mess to distinguish, but in principle, you can. So yeah, then with this, you can compute the number of events in the Earth. And yeah, for normal ordering, what we have is now that nu2. So it increases the number of events compared to nu3. Like neutrinos are nu E produces nu2, compared to neutrinos produces nu. So these green lines are the ones with NSI. So what is the mass ordering ambiguity that I'm talking here? Is that you see like the green line here, I just equal the blue lines here. So the normal ordering in the presence of NSI is just identical to inverted orders without NSI. So if you are detecting a peak and you are thinking, okay, this is definitely inverted ordering, that might be just normal ordering in presence of NSI. Yeah, let's avoid that. And it comes because in the standard case for inverted ordering, nu is and for NSI in the normal ordering. So just to summarize the picture, so basically we have the two MSW resonances intact, let's say. And we are adding the effect of the new one before. Before. Yeah, and in this case, in our case here, this will convert new to new tau. But of course, you can do that to new blue also. Like, it would be basically the same. What about epsilon tau tau bigger than 0.33? It's simple. Like in this case, the term related to new tau will be always bigger than term related to new e. So new tau will be always, there will not even be a resonance. New tau will definitely be always more energetic. So new tau will be always produces the heaviest one. And new e as the second heaviest one. So the results is not change. And you don't even need off diagonal elements or anything. That's so, and what if the off diagonal elements vary? So as the off diagonal elements vary, this is the red curve. Like you can go from the blue one, which is the standard case, to the fully NSI ones, and as so to go to the fully NSI ones in off diagonal element of the order of things with the -5 or higher. If they are smaller than these, like there will be a television. So just to say that, I mean, the sensitivity of DUNE using neutrinos is of order 0.1, because with 0.1 you can satisfy these criteria. And most of the global fluid bounds are like around 0.4. So it's a good feature of DUNE. Am I right? So, and this I have a profound impact in the nuclear component. And if I can get anything out and this go to the proto-neutron star, don't exploit this beauty of order. NSI of order 10%. And this phenomenon is supposedly ambiguity between the normal and the
We should probably estimate that before, but on your slide 27, I think, where you show this peaks, yeah, actually this one, yeah. No, the next, no, previous, this one, right? Yeah. So so we're looking for this peak, but it comes within 5 milliseconds, right? And well, I suppose DUNE resolution is good enough for that. But neutrino flux goes through the Earth, right? And there can be coherent neutrino scattering with significant enhancement of the cross section. And neutrinos can be scattered from the Earth material back to the DUNE detector, right? And then the effect would be on the order of 40, maybe even 100 milliseconds. But the timing for those neutrinos that are scattered back, for example, is going to be quite different, right? And therefore the peak will wash out. Have you estimated that effect?
We said, why is a
So neutrinos go through the Earth, right?
Yeah.
And then some of them can be scattered back due to coherent neutrino scattering. Cross section is not that small. It's small, it's not that small. And then they go back to your detector and then detect it by DUNE, right?
Yeah.
So then can you distinguish those? And
yeah, I mean, in principle, so that would be the same thing people do for solar neutrinos. They call day-night asymmetry. It's like, so during day you detect neutrinos directly from the sun. During night, you have a little bit of enhancement because of neutrinos go through the Earth and they go additional oscillations there in matter. And then you see some, I don't know exactly how, what is the prediction of this. Little enhancement with some new oscillations.
no, my problem is this, the timing will be different, right? All these neutrinos that you're looking for, they're supposed to come at the same time to your detector. And this is how you know, okay, there is a peak there, it's time. But those neutrinos that are scattered over the Earth, right? even though they travel with speed of light, but they have to cover radius of the Earth, therefore timing will be different for those neutrinos, and then you push out the speed.
Well, I mean, what you mean is really scattering, like neutrons are go scatter somewhere and go back to.
Exactly, they go through the Earth's material, right? They scatter somewhere in the Earth, somewhere, and then they go to your detector, but the neutrinos originated from supernova, right?
Yeah.
So they're related, but they come later because they were scattered somewhere 6,000 kilometers away.
Yeah, as far as I know, the most significant effect of scattering inside the Earth for neutrinos at these energies is not like really scattering this way, is the coherent forward scattering. Like they wouldn't change the direction. They would coherently scatter in the whole matter of the sun. These would act as a new matter effect. Like, so you have a profile which is like neutrons come through supernova, go to vacuum, enter another matter like supernova, and go additional oscillations. I don't think, like, I cannot do estimations, but I haven't estimated it, but I'm quite sure that at these energies, otherwise people would have talked about this for the sun also. That's what I mean. So for these energies, what's really relevant is to compute the day-night asymmetry. If you are on the other side of the Earth and the source of neutrinos is on the other side of the Earth, neutrinos go through the Earth. The Earth matter is like, water is like 1 gram per cubic centimeter. So you are back to one of these densities here, right? 1 gram per cubic centimeter. Then you are here. Then you suffer a new matter effect. Remember the low MSW resonance. It happens for in this case 1 to 10 grams per cubic centimeter. So from neutrinos going through the Earth, it would go through quite a bit of matter effects, the usual ones. But people have estimated. I mean, I haven't done these.
So for solar neutrinos, the effect is the day-night asymmetry is around 3%.
Yeah, 3%.
Which is probably not going to be that
Change drastically.
drastic changement. And
But-
plus, it might be because the burst itself is so like timing specific. It's either going to be going through the Earth or it's going to be either day or night. It's not going to be both of them different. So I think your question is how it changes if it goes like through the Earth's matter.
No.
I think what you have in mind is supernova,
Yeah,
detector,
yes,
or
yes,
neutrinos.
and scatter back, and then timing is screwed.
The probability of any given neutrino to interact twice like that would be 0. Or very, very, very close to 0. Because if you look at the event rates that he's looking at, the incident wave of neutrinos coming in, you're only gonna get order 100 events. The probability of any neutrino going, interacting, turning around and interacting in the detector, you're gonna pay a penalty factor of 10 to the minus, something very, very big. And so I think that's gonna be negligible.
Okay. Because of the cross section.
Even though the
Cross section is too small, even though it's enhanced because of coherent
Yeah.
scattering, right? It's too small, right? That's what you're saying, okay.
So, I'm wondering, like, in the core of the supernova, there might be a muon density as well. So, would there be any enhancements if you include it, or is it too small compared to?
Yeah, no, good question. Like in the core of the supernova, there is a muon density, but this is a very recent development. But it's really inside the proto-neutron star, like very in the core. At that place, neutrinos are still not free streaming. So it doesn't make sense to really talk about matter effects there because like the mean free path is smaller than it's like smaller than the size of the proto-neutron star, and like neutrinos would be being absorbed and re-emitted and so on. So when I talk about matter effects, basically neutrinos have left the proto-neutron star and they are like free streaming. So they have a mean free path that's larger than the star itself. But let's say that you have muons there, then it still wouldn't work. Let's say that there you have muons, and you want to compute this matter potential. Then you change, like it would change a little bit. But if the number density of muons is not higher than the number density of electrons, the results would be the same. Even because, you know, like at high density, like above 10 to this 7 grams per cubic centimeter, there is a correction to the matter potential between mu and tau. Because usually we say that the matter potential of mu and tau are the same, because there is no tau or muon free in the environment, only electrons, so only the electrons are distinct from the other. But you have a correction, I think a loop correction, that because of the mass of the tau being higher than the mass of the muon, like you get a little bit more of potential for the tau than for the muon. So above 10 to the 7, already mu and tau are not the same thing. So these already be taken into account. If you add muons or taus to that initial region, you would be a correction to these. So the results wouldn't change so much. Yeah. Unless you make this number of mu and taus higher than the number of electrons, then you would make like these neutrinos being produced heavier than the electron neutrinos. Then the results would change. It would be very much like NSI.
Can you go to your sensitivity figure right before the conclusions? What did you assume about the mass of the and distance of the progenitor?
Okay, sorry. The mass is something that's 18 solar masses, which is the progenitor like that the Gaussian group gives, and the distance is 10 capacity. So it's,
Okay.
so it's a galactic thing. But actually in the paper we do a small chi-square, but we don't. So we do kind of a shape analysis. So basically like the normalization that is related to the distance, right? It would change depending on how you vary this distance, 10 parsec, 5, 15, and so on. But the shape would be still pretty.
But at some point you won't be able to tell, statistically, you won't be able to tell the difference, right?
Yeah.
The other question I had was in making that figure, did you marginalize over mass ordering? Or did you assume that that was known?
I assume that was known.
Okay.
Not marginalized. So basically, yeah. Yeah. This is a very simple, like very.
Sure, but in principle, if you marginalize over the mass ordering, then this confusion may very well just wipe away your sensitivity.
Swipe away this.
Wipe it away,
I see.
make it vanish.
Also, too, could those orderings be like ruled out by like CMB or double beta decay or something? I don't know. I mean, I don't know exactly what parameters are used, but it might be such that some of that, you know, those inverted orderings are already tested by something.
Yeah, I mean, that's good actually. Like if you know the ordering, then you can kind of have some sensitivity to NSI.
Yeah.
Otherwise, you won't know. But as long as you know the, like, let's say you already know the order, that's what we assume. Then you can kind of.
Any other questions? You're doing supernova identification at DUNE. You wouldn't be able to identify it was a supernova neutrino based on energy, right? So you're just doing it based on number of events and the trajectory of the neutrinos entering the detector?
To know that it's a supernova neutrino, even it's timing, right? Like you have other observables, you know that the supernova has exploded. You have a sudden increase in the number of events in a very small period of time.
Right, so it's number of events and trajectory all within a certain time, but you're not gonna be, you can't do any energy distinguishing, right?
No, in principle, yeah, these energies are, let's say, all types of neutrinos have MeV energy, so you cannot distinguish supernova neutrinos on the basis of energy. But yeah, it's like the timing information, I think, is the most important one. And correlated with other detectors that have directionality And other observables like you see in the optical telescopes and supernova and so all of it value with the supernova.
Let's give another round of applause for you. So we were trying to of the direction. Actually, we are not of the direction.
I have you on
Direction.
spreadsheet.
Then we saw this.
You don't want to.
And again, it's we're basically trying to see. So there are some plots which